So a couple quick announcements to start. One is the pH lab is due tomorrow, and apparently everybody waits till the last minute to do it. So I'm getting frantic emails and stuff and people during office hours, which are really good questions. So the purpose of the lab is for you to be thoughtful about it. And some of you are going to have the things in your house where you will get the whole rainbow, and most people don't. I think last year, actually, only 2 people were able to find all the colors. They actually ended up Googling to figure out how to make the orange color, and it was a mixture of 2 things. I wouldn't have been able to do it because the 2 things were definitely not in my house. One was something like aspirin or ibuprofen or something, and I forget what the other, or maybe that's what it was. Maybe I just gave the answer away. It was a certain brand of aspirin or ibuprofen gave, and it was probably Advil, because isn't Advil the little red pill? So it's probably the coating on there.
Yeah, I tried aspirin last night and I got a really bright pink.
Yeah, aspirin should be acidic.
Yeah, it was like Pepto-Bismol color.
Oh, did you do?
I didn't use Pepto-Bismol, but it looked like I did.
No, yeah, I used to do that when I would go to elementary schools and do this with the kids. I also had diarrhea medicine and stuff because they found that so disgusting and would all have to try it. But yeah, I think it was actually the Advil. It had to be if you had Advil, and I think it was the coating on it. But really, I'm looking more for in the post lab that you're being thoughtful. And if you didn't get yellow, it's really hard to get yellow because yellow is a pH of 14. You should be able to think through what the answers are. And as I just said, it is a lab that is done with elementary school or middle school. And so it's just to give you the idea. Reminder, you can get a bonus, write poetry. Some of you have found your art of poetry if you can make the rainbow, and if you make a beautiful dish with the leftover of your cabbage, and take a picture of you with your wonderful food that you made. Presentations are like really soon, so Monday or Tuesday, and have fun. Let your personality show, and you can dress up like your famous person. You do want to get the science in there. We're emphasizing the chemistry, the contributions to science, but you can also have fun. And with the paper, you can also have fun. So it's 3 to 5 pages, or three to, some people go more than 5, but it doesn't need to be that long. I did want to comment. So in case you didn't notice, your exam showed up like around 8 or 9 o'clock last night, your celebrations. That the points in the class are distributed. So when your exams at the end of the term, once we get there, your exams are only going to be about 40% of your grade. So your presentation paper, that's 60 points. That's going to give you all a huge boost if you put some time and effort into it. And anyway, I look forward to that day. We do have class on Monday, and there are assignments due Monday, and I'll open that folder. Juan, you'll remind me at the end of class. It's there. I just forgot to open it, push the button right before I came in here, started this. Sorry. Oh, somebody did send me a picture today. I was actually like the highlight of my day right now. When I opened my email, there was a picture from somebody who's not in this section, but who'll be watching this. And it was them in their backyard by their little stack of stones. So they got 5. Which is much more than I can get. So Major, that's what you're going for. See if you can get to 6. But that's due by Sunday at 6:40. And as I was having a conversation with somebody earlier, they're all little bonus points, but they start adding up. So take advantage of the opportunity for a bonus point. I'm disappointed nobody dressed up as a mouse. All right, we're doing titrations today. And I bought this shirt. I found it at Goodwill specifically for the lab we would have done yesterday. And so it breaks my heart because you don't get to see this, but it is the victory of titration. We would have done 3 of them this summer, and you guys would have become master titrators. And by the 3rd one, you would have all been like this guy. There is the little guy here who is what most of you look like at the first titration lab, which is, oh no, I missed it. And that's the color of the shirt I'm wearing, is when you miss it, that it turns this color. But we're just going to do the calculations. And the lab, by the way, that's due tomorrow. Again, have fun. I'm looking, just put it into your creative data table and answer your post labs. I can do office hours tomorrow. I'll open them up at 1 o'clock. And if nobody's here, Zoom will kick me out. And all right, titrations. So titrations are wonderful. This first page is just you can kind of listen, make notes. We're not going to do this titration. We're not going to see calculations with this one again, because it's a strong plus a strong. We're going to spend time on the next 2 pages, which is a weak acid and a strong base, and then a strong acid and a weak base, because that's usually how it's done. But this one, it's just really simple math, because it's a strong and a strong. We don't need any Ka or Kb values. So it gives us a nice way to look at the whole thing. The initial pH, we haven't mixed anything yet. So since this is a strong acid, all we have to do is what?
Negative log of 0.1.
Yes. Is that Sumner?
Yeah.
Thank you. So the negative log of the strong acid. This is the strong acid. Now, this is a question several of you were asking during the office hours, not about this one, but something you were kind of hinting at it. This must be molarity. When you plug into pH, it has to be molarity, which we will be in for this page because we're not doing mice charts. All right, we're going to go ahead and write the reaction so we kind of see. Actually, this one we're going to do in mice chart. So we're going to have the HCl plus the NaOH. And we will get NaCl plus H2O. Now, this one, neither of the products matter. Because sodium chloride has no effect on pH and water is water. We're going to make a mice chart just for the practice of it with this one. So the I is we need the initial moles, and the M is just the math setting up for that. So to do the subtraction, the change is the change in moles. So it's a limiting reactant, right? Yeah, technically everything we did last week, we were supposed to do in moles and then go back to molarity. But again, the volume never changed up through the first celebration. So we could kind of just leave it in molarity or ATMs. The volume is changing now, especially with titrations, because we keep adding something to it. So we take our volume times the 0.1 molar. Depending on your skills with milliliters, with milli, you can either take the 50, the milliliters, you'll divide by 1,000. And that, let's do it up here. Anytime if you take the milliliters and you divide by 1,000, that will give you the liters. Some of you do it a different way, just be consistent, but if you're having trouble with it. So this is 0.05 liters. About half of you, you can just do that by moving the decimal. And you guys know who you are. Some of you know, you look at 50 mils and you go, that's 0.05 liters. You have to be in liters times the 0.1. We have 0.005 moles. The chart has to be units. Some of you know you move your place values funky. So always divide by the 1,000. So like the 20 milliliters, you'll divide by 1,000 and that will give you 0.02 liters. Now the other comment, and kind of respect that half of you are like me and you leave the 0 out before the decimal. And some of you have to show it. And so do it the way that keeps it straight in your brain. So if you have to show that 0, then please show it. The NaOH is also 0.10 molar. And we get 0.002 moles. Okay, the hardest thing with this, and a couple of people for 25 years, I've had this with students, these zeros are going to drive all of us crazy. Your teacher is going to, right? Just so be careful on the place value. So it's 0.005, 0.002. So missing a 0 or having an extra 0 does make a difference. All right, the big difference from yesterday with buffers and today, there's a 0 initially on the product side. So titrations, you're starting with only the reactants. A buffer is, hey, we're already there. We've mixed the two things. So in a buffer reaction, which is today's study set we'll look at later, we will have on both sides to start with. But in titrations, you do have the 0. Right? We subtract the smaller one, the 0.002 moles. So almost always you're strong. What you're adding, in this case, the NaOH, is your limiting. Sorry, I should say minus 0.003 moles. And then on the product side, you would add the 0.002 moles. Somebody asked me this question at the end of class, and I kind of hedged around it. We'll see it here. It doesn't matter, though, for this problem, because the NaCl is neutral. So we're going to end up ignoring it. Now, back to the question that I'd asked. This is a strong acid in this case, so we can just plug it right into negative log to get the pH. However, we're plugging it right into the negative log. It's going to be has to be molarity. So if it's a strong, that is something you have to be careful of. That is moles. So what is the volume?
70 milliliters.
It is 70. It is the total volume. So we started at 50. So this little guy up here, so this had 50 milliliters is the idea of a titration. When you did your 221, so there's like 2 of you, actually 3 of you, who actually got to do a titration, or actually like maybe 4 of you who took 221 real. And then here you're adding the NaOH. So you now have the 50 plus the 20. One of the things as we go through this 50 milliliters doesn't change for the initial of our HCl for all the steps we go through. So this would be over 0.07 liters, the total volume. So that has to be our total. The NaOH volume keeps changing. And this was actually, has always been. At this next point, when we do 40 milliliters of NaOH, it will be the same chart. I'm going to actually keep moving on. This number here would now be 40. So it's not 20 plus 40 more. This is saying at this point. So the NaOH, it's just whatever number I give you. That's the volume of NaOH we're at. The HCl, it's always 50 mils to start with. I'm going to skip though. If you want, you can try that problem and you can see our pH. Pick a different color. It started at 1. Here we're now at 1.37 and now we're at 1.95. So the answers are going up slowly, but only slowly because we still have more strong acid. We're adding the base. We haven't overwhelmed the acid yet, so our pH is staying really low. It's barely changing until we get to the equivalence point. And this is the key of titrations. This is the point of titrations. This is the magical moment. This is where the moles are equal, that they are perfect. So our moles of our acid, of our HCl, and we're going to do an abbreviated chart, but our reaction is the same. The moles here is our 0.005 moles. So what you'll see on some of these problems, it will just be 1 point in the titration. Some of them, like your worksheet for next Monday, it's all 1 titration. So this number just keeps being the same, our starting number. So you don't have to keep showing that step. At the equivalence, this must also be 0.005 moles. There's only this 1 point, and that's where that perfect color shows up. So what is the limiting reactant? Neither, because it's the perfect stoichiometric ratio. It's the perfect moment. They both are gone. They've completely reacted. All of the moles are now on this side. Only if it's a strong acid and a strong base, the pH is 7. Because the conjugate is neutral. That's not going to be true for any of the other problems we do. But sodium chloride is our conjugate, and it has no effect on pH. There's no Ka or Kb value. So 1As, again, they can't make complex ions, and chloride is the complement to a strong acid. All right. We're going to do one more. Sorry, I was trying to decide if I wanted to do this problem or move on, but we'll do it on this page. So again, our equation, HCl plus NaOH. Write your equation and do our mice chart. Questions? It's on the next page. It's similar. The mice chart is the same idea as what we're doing here. The difference is we'll have to use Ka or Kb value depending on what we're starting with. All right, so my initial for the HCl is 0.005 moles. That number holds true for the whole titration. Again, it's what was in the flask, and the amount of NaOH I've added is 60 mils. So 0.06 liters times our 0.10 molar. So again, this is the volume that we're at that point. That's 0.006 moles. All right, this is not the magic mouse moment. This is, we missed it. We're past the equivalence. Post or past, I don't care. So we're after the equivalence point. The limiting reactant is your smaller number, the 0.005. So the HCl has been neutralized. It's been more than neutralized. So we're going to have excess. This is of our strong base. That is the excess of the strong base. So how do I find the pH? Oh, I left, like over here, we would have points plus the 0.005 moles. I know I'm not lined up. My writing skills are not allowing that for some reason. But as I mentioned, this side of the equation doesn't matter on this page because it's all neutral over there. NaOH, strong base, NaOH, you can plug right into POH. Except, back to the question I asked a couple moments ago, has to be what units?
Molarity.
Molarity. All right, so we have to divide by the total volume. So what is my total volume here?
Is it just 60?
60.
It's 60
plus 70.
No, 60 plus the original 50. So it's always the original that you started with plus how much you've added. So thank you. Somebody said, like they see it. So the 20, the 40 here, whatever number it was, which was 50, those are just at points. We're just like stopping it for a minute and taking a bird's eye view or mouse eye view. So this is going to be 0.11 liters. Sorry, that's the 50 milliliters plus the 60 of the HCl and 60 milliliters of the NaOH. You don't have to tell me that detail. I'll know that you got it. So it comes out 110 divided by 1,000, so 0.11. And we would do negative log of this. That will give us our POH. And then you all know, you would just say, this is my pH. And then you don't have to show me the step, I'm sorry, the POH, and you change it to pH. My question, why does that answer make sense? Because I'm going to ask this at random points. So why does that answer make sense? 11.9.
We've been adding more base, so it's more basic. It's about 7.
Yeah, we have excess of the base. All of these up here, our first 3, we had excess of the HCl. So our pH was really low. Now we have excess of the base. So excess strong base. So once you pass the equivalence, so it's post-equivalence, excess of the strong base. So I'll ask more than does it make sense. I'll say, does it make sense? I'll say, where are we? And you'll say, we're after the equivalence point. I have excess of the strong. So in this case, it's a strong base. So my pH is really high. Right. That was just to give us kind of the idea of what we're going to do. The additional piece on the next page, one is we're going to have to write the equation smaller because then we're going to plug into KAs. All right, so the very first one, it's now a weak acid. You guys just did this on your celebration. We were doing these last week. Only the weak acid is present because it's initial. It's before we started adding the stuff, in this case, the NaOH. So this is what's in the flask, the weak acid. Whatever I say first, and we're adding this, that's a great picture. So this, you would state your whole formula, but this is an x squared over 0.1. Only the weak acid is present. If there's only one thing present, it's x squared. You solve for x equals your hydronium, and then you do your negative log of your x, right? And then your teacher will ask you, why does that answer make sense? So you can either go through the math or somebody can tell me why this answer makes sense.
Because of the power of the Ka, it's within the 0.5 range.
So actually, thank you for answering it that way, Paul. That's going to be the answer to the next question. On this one, it's not. So his answer is the answer on the worksheet that's due today, which is buffers. When we're dealing with buffers, the pH will be around the Ka's exponent, which is 5. And we can see that's going to happen on these next ones.
Oh, I see it.
Here, all I have present is an acid. pH should be low. So only acid, so that equals a low pH. And so all I'm looking for, I'm not looking for this over analysis, although some of you like to do that, which is great. Actually, sometimes you do, you hit it right on the nail. There is another part to this. Here we got 2.87. It is 0.1 molar. You can try and math if somebody wants to think about this. Here, it was 0.1 molar and all we had was the acid. And I got a much lower pH, a pH of 1. So why here, if I have the acid and it's 0.1, is my pH 2.87?
And this problem, it's a weak acid, and the other one was a strong acid?
Yeah, strong acid completely gives up everything. This is a two-way equilibrium. And so only like 5% of it is ionized. So the weaker the acid, right, the higher the pH. It's not, so perfect. I think that was Perry. All right, so I'm going to pause us and give you a chance to write your equation. It is your acid plus your base, and to try your mice chart. You want to do it because we are going to plug into Ka. It is not an x squared. Once you add the strong base, it is not x squared. It's going to be a buffer problem. So I'm going to pause us. So if you've got it, keep going. Or so our acid plus our base. I always put the piece I started with, the weak acid first and the strong second, so the NaOH. And again, I like to do it on the handouts. Some people like that. Some people can write smaller, but you can always do it on another piece of paper, especially if you don't have a printer. So whatever works for you. These are one-way reactions. So these are not the K expressions. These are so we can get the numbers we need to plug into the K expression. That's one of the big concepts. So this is the hydrogen and the sodium. They're going to switch places. And you can put the sodium first or last. I sometimes put it first, sometimes put it last. And H2O. We're going to ignore the H2O. It's neutral. It doesn't have an effect on our pH. And then we do our mice chart. So again, get to liters. So dividing by 1,000, or move your place value by dividing by 1,000. So 0.05 liters. And yeah, in the notes, I picked nice numbers so I can usually do the math in my head. So 0.05 liters times, so it's the volume times the molarity. So be careful, don't ever abbreviate moles as M, because that will confuse you. So that gives us our 0.005 moles. Again, this number we're going to use in every chart on this page. So that's nice. All right, our base is, this number is going to be different for every single one. So the 20 mils, 0.02 liters, and actually something I see about a handful of people do. And again, it has to do with our brain. If it helps you to make columns, to actually make the columns, go ahead and the rows, go ahead and do that. That can actually spatially help a lot of students. And then there's people like me who that doesn't make a difference. Right, 0.1 molar, which is 0.002 moles. A reminder, your product side is 0. not a buffer problem. The change is our smaller number, which is almost always, not always, but almost always what you're adding. The nice thing when it's a question where I give you multiple parts like this, you're going to know, because it will usually be the last thing, and I'll say, oh no, you messed up, or whoever did it, they messed up. All right, so this is 0. You can just cross it off or say 0. This side, we're now at plus 0.002 moles. And this is 0.003. All right, we're going to label. This is my weak acid, and this is its conjugate base. It is going to be a ratio problem. The total volume does not matter because they're both going to be the same volume. If you want volume, if you see that when you have both pieces, you can ignore the volume. If it's x squared, if all you have is the strong, you have to be in molarity. If you see that, great, go with it. They have to be the same unit, the weak acid and the conjugate base. So you want to state, I'm just going to state it this one time to make sure. It does make a difference. So you're going to state your piece, your formula, right? That really helps, because then you can say, okay, and labeling which is which will help you. So our Ka is up here. So we'd have 1.8 e to the -5, or however you write it, equals the conjugate base is the 0.002. X is this, the hydronium, and this is 0.003. And cross multiply, X is your hydronium. It is molarity. All the numbers in here are molarity, and so the X is always molarity because these two, their units are going to cancel. So if they're mole and mole, their units cancel. If you did the volume, they both would be divided by 0.07 liters. So because you have the two pieces there, that's why it doesn't matter. Again, if you see that, you can use that trick where you can ignore the volume. If you're still not sure, then when in doubt, or ask me. All right, you solve for X and we get a pH. Now, back to the question I asked earlier, Paul answered it. At this point, we have a buffer. Once you start adding, so we're at the point on these two problems on 5 and 7. I love how my computer numbers things. If there was somebody in our class the one term and she commented, she sent me an email saying, I love all the angel numbers. I didn't realize that, but my computer apparently renumbers everything. So these two steps were in the buffer zone. That's what I call it. So you have initial, so that was here. And then between, you have the initial, we'll have the equivalence. In the middle, this is what I call the buffer zone. So you're adding the NaOH, right? But we're not where the moles are the same. We haven't crossed this out yet. These two are not the same. And then we'll get to the point where we're post. So the buffer zone is pre-equivalence is the other thing. And so in the buffer zone is where you can keep it as moles. This is where the answer Paul gave me. The pH is going to be around the exponent of the Ka because you have both pieces present. All right, the equivalence point is where the moles are equal. The half equivalence is where half of the moles have reacted. And so you can, for this one, I gave us a little bit of space. I'm going to show you to prove that that's what's happening. And you never show work here again, except for one step. That's my negative pause. This guy is 0.005 moles. That's my initial. If I'm halfway there, half of that number has reacted. So I'm now at half that number. Which means the other half is on this side. Again, you don't have to write this, but if I don't, then somebody asks me later, can you prove it? And so I'm just going to do it right now. So this is my weak acid. This is my conjugate base. You can kind of just sit back and listen. They're equal. So in this formula, our Ka formula, the conjugate base and the acid are the same. So only at this one point, at the half equivalence, not the equivalence, the half equivalence, since the concentration of the acid equals the conjugate base. It's like the perfect spot, right? Since these are equal, circle it. That means that your Ka equals your hydronium. So basically they cross out. So all you have to do is negative log, which means your pKa equals your pH. That is at the half equivalence. That step that I just put the stars on, that's the only thing you have to say at the half equivalence. You're going to be given a very small place to show that. You'll just say the pH equals the pKa. You negative log your Ka, and you'll get 4.74 for this question. Back to how Paul answered. The answer makes sense because I'm right at that exponent. I'm right around 5. So our pH is changing just a little bit. It's only changing small amount as we're adding. It is slowly changing, but not much because it's buffering. At the equivalence, what is equal?
The moles of acid and moles of base.
Yeah, another way of saying it is the moles of the reactants are equal. So you want to be careful because I'll ask like what's equal at the half equivalent. That's where whatever you started with, your weak equals its conjugate. But here, how Perry answered was great. So this would be, and it can, as long as you label your pieces. A comment that came up yesterday, and I did it and didn't even realize I did. I leave the water off in my balanced equations sometimes because it doesn't matter. If that drives you crazy, then just keep it there. But we never do anything with it. So I have my acid plus base. I do need my conjugate because this is important. And we're going to do a mini mice chart. So we're really just needing the I part. These are 0.005 moles. Now, some of you are going to have to make your full chart and show the minus, but really they both canceled. It's all on this side. So you can just cross them out. It's all over here. Now we have a problem. We only have one thing present. So at equivalence, there's at the equivalence, Since these both cancel out, only the conjugate is left. It's an x squared problem because you have only one thing left. This is like that last question on your celebration. You have, this is a base. You have to use KB. If all you have is the base, you have to use KB. So the study set 5, worksheet 5, it's all about buffers. Buffers have both pieces. You can use KA or KB, it doesn't matter. Initially at the equivalence, only one thing is present. You have to use what's there. It's a base, we have to use KB. So just for practice, we'll write our formula, KB equals hydroxide conjugate acid over the base. This is now going to go in here. So write 10 to the negative 14 divided by your Ka is your Kb. It's going to equal x squared. You have one other problem. You cannot use moles because you no longer have a ratio. You must use molarity. So make a note to yourself. And again, if it's x squared, if you have only one thing there, it's molarity. If it's a ratio, you can leave it in moles. And the answer that pops out is molarity. You can ponder that. So what's my volume? So there is usually an extra step, and probably shows up on the next page, where I ask you, what is the volume of the NaOH? This question is really simple because I made the molarities the same. I made this 0.1 molar and I made my NaOH 0.1 molar. So that would tell me my volume's the same. We'll solve for volume on a later one, but I have 50 mils here. This guy's also 50 mils. I know that because if you take, yeah, we'll do that because you probably have seen enough of my numbers to know they're never going to be 0.1. I actually had somebody I work with who commented, they were actually very grateful that I did that with students because in the real world, you're not going to have 0.1s and 20 mils. Everything's, you guys have lived in the real world to know. So our total volume is 0.1. When you solve, so this number is going to go down here. My recommendation is you go back and redo this page, like, and see that you can get the numbers. So when you find X, it's Kb. So X is your hydroxide. So you either going to have to write smaller to fit everything. I'm adding a lot of notes here. Some of you are going to be fine, and some of you know you're going to need a whole page to do each problem. All right, so then you do your negative log, and kind of, Paul, you asked this question earlier, so then there's the extra step. We have to change the POH to pH. I don't need you to write that step out. I need you to tell me your X value, whatever it is, that's your hydroxide, and then we get our pH. pH makes sense. It's a base. The acid is gone. All right. This one, when you get to excess.
Sorry, quick question.
Go ahead.
Quick question. Where did you get the 0.1 liter from the total volume?
It's going to be 50 plus 50. So that's 100 mils divided by 1,000. Major, on a later one, I'll go through solving for the volume. Right now, I'm like getting the mole part. Yeah, when we get 2 pages from now. For the excess, this is, we did this on the previous page. You just, well, we can go through it. I'm going to pause again. So write your equation, figure out your excess, and then if you want, you can look at the next page and see what you can do there. Or you can take a 5-minute break. And so again, it's kind of like busy work and stuff. I do hopefully give more space on there. So a couple key things. So the equation keeps being the same. So like on your next celebration or your study set or whatever, do the first one. You can always, because it's going to be due on Monday, you can always take a picture of it and send me an email over the weekend and say, hey, can you look at my first one and tell me if I'm setting it up right? And I give you yes or type in something to look at. This initial moles of your week, whatever you started with, that number is the same the whole way through. So every chart has that 0.005 moles. That was something for a lot of students. And like right now, your teacher's doing it, but that's something that will help. The NaOH, we're at 60 moles now. So you're not adding volumes for that. It's just 0.06 liters times its 0.1 molar. So the only thing from the NaOH that you keep bringing down is the concentration, the 0.1 molar. The volume is different at each point. And yeah, so this is, and this was your teacher using very simple numbers to work with. Our limiting reactant is the smaller one. So you subtract the smaller moles. That guy cancels. And again, if it helps you, or to at least put a line so you have on the left side and the right side, whatever works for you. And on the product side, and again, I see about half the students do the lines because that really helps them. We have plus 0.005 moles. This is subtracting, so 0.001. All right. You want to always take a deep breath and label what each piece is. So this is my weak acid. It's gone. So no more Ka value. This is my conjugate base, but this is the strong base. Although the conjugate base does affect the pH, we would have to go out several place values to see the effect. Really, if you're really bored, you can go through the math and figure out what the hydroxide is from the conjugate base. You cannot add pHs, but you can add hydroxide and then add it to the hydroxide we get here, and you'll see it's not enough to go through all that work. So this determines pH. After the equivalence point, once you get to the oh no moment, this is excess of a strong base, and that determines your pH. And since it's a strong, you can just plug right into negative log of your strong base equals your POH. However, that's the NaOH. I will always be using NaOH for your strong base to keep it. This has to be 0.001 moles over the volume. We need a total volume. So what's my total at this point? This I gave you the numbers.
0.11 liter.
Yeah. So we had 50 mils, our initial, and I added 60 more. So I had 50 mils, which was my original, my initial, at the very top of the page. And then I added 60 more mils of the NaOH. So 110 or 0.11, that We'll plug in, we'll get the POH, change it to the OH. Makes sense. pH should be really high because it's strong. It's kind of back to the question I asked at the beginning of the page. A strong acid or a strong base is going to be extremes for your pH. On this previous question, we do get a pH above 7 because we have the conjugate there, but it's not as dramatic as this pH. We have excess of a strong. All right. We are going to draw the curve. So hopefully you have another piece of paper. I didn't want to just put a blank page because then your printer just prints a blank page. So draw your X and Y axes. pH is your Y axis, and NaOH volume added is our X axis. And we know some of our points. We know our starting point was around 2.87 pH. And we know our end point is way up here was what, 11.96. It's not a straight line. So it is, and it initially has a slope. It's a gentle slope. And that is because this is the buffer zone. This is where you have the acid and the conjugate base. It's a ratio, and that ratio keeps changing. As we keep adding more and more NaOH, it's slowly going up. I made this more dramatic than it might be because you don't want it to be too dramatic and then something happens. So at this point, that's why I stopped right here. At this point is the equivalence, and this is when we were at 50 milliliters. This is the equivalence point. This is the point. This is where it's a bummer we're not in lab. One drop, the pH goes all the way up. This is a cliff. If you want, you can make a guy climbing up a cliff. Whoops, okay, hang on. He's climbing. It's like a 5'10", 5'12" climb. It's like serious. This is a serious climb. All right, you should have your Sherpa guide up here holding you. That could be me, smiling. You don't want me. You would want a real Sherpa holding you, pulling you up to the top of the cliff. This is what happens at equivalence. The moles are equal really for a moment. That's the femtosecond, and then you have excess. So at 50 mils, we can label our point. We had a pH at the equivalence 8.72. The equivalence is roughly halfway up the cliff. The equivalence is the cliff. It is steep. It is straight up and down. Not actually, but it is close enough for our. You could also make it a waterfall. You can do lovely drawings here if you want. Or you can just make the same curve every time. So here it's like you're gently walking nice and calmly up the sloping path. If this is 50, we can do our halfway, which is 25. So this is going to be my half equivalence. So the half equivalence means we're at half the volume, not half the pH. So we can go back and look at our calculation. Half equivalence, we had 4.74. My graph is not perfect. So you can kind of put your dot, dot, dots. This is around 4.74. And we actually have another point we did. So again, we start gentle and then straight up. Okay, up here, this is post equivalence. It's where your Sherpa guide is holding you up. This is where we have excess NaOH. At the equivalence, what was the only thing we had at this point?
The conjugate base.
Flex.
Yes. So only the conjugate base, only the conjugate. That was Christian. I don't think I have your name up there yet. I'll write you up there. All right. We did one other point, which was at 20 milliliters. So we can roughly put that in. It's going to be close to 25, right? And the pH was close. It was 4.57. So sometimes they're really close like that. And then you can have fun drawing there. Questions? We're going to add to this. All right. So the red line is the weak acid plus the strong base on mine. If you have color, use a different color. If you don't have color, use like a dotted line or something. So I'll do it as a dotted line in green. I'm going to do the strong acid plus strong base. This was 2 pages ago. What's different? This is the question Perry answered, right? The strong acid starts lower. So we're going to actually start down here at a pH. It was actually 1. So this is my strong acid. And another big difference is it's pretty much flat at the start. Or flat before equivalence, sorry. Because it's a strong plus a strong. Anybody, any idea why it's flat before the equivalence? So it's like when I said it's gentle sloping, this is like we're walking along a meadow. It barely changes. So I'm gonna go ahead.
Oh, I was gonna say, is it because the strong accident has to do anything with the buffers?
Say that again.
Is it because the strong accident might have to do anything with the buffers?
It's not a buffer. Is that what you're saying? Because it's a strong. Yeah, strong acids don't make buffers. It has to do with the conjugate.
The strong acid.
Go ahead.
Never mind.
The conjugate was sodium chloride. The conjugate was neutral. So here, we keep getting more as we increase the conjugate base, right? And we're decreasing the acid. This ratio, we keep increasing how much conjugate base and decreasing the acid. The pH is going to keep changing. Here, we keep making more and more conjugate base. We're decreasing the acid, so the pH does change. It changes by about 1 point, but that's it. The other big difference is at equivalence, because it's sodium chloride, at equivalence, our pH is 7. That was from that previous page. And that had to do, again, the conjugate had no effect on pH. So the things that are similar is we see a sudden change. Our equivalence is here at 7. Well, that's the piece that is the same is post-equivalence. So what they have the same is sharp or cliff change at equivalence. It's one drop and you see this change. Computers can do it for us and give us these beautiful curves, but this is one where the visual of seeing the color change, and it really is. And this is where students will turn it and they'll end up adding 5 mils instead of 1 drop. And that is the old ABC, like Wide World of Sports, like the victory. I can't remember the slogan. So the change at equivalence is dramatic. Sharp cliff, dramatic change. And post equivalence is the same. Why is it the same post equivalence? The answer's up there for you. Because after equivalence, you just have excess of the NaOH. I want to make a quick comment. It was a question that Major asked me a half hour ago. It had to do with the volume. The volume is going to be different for every problem. So these numbers and these numbers will be different, but the idea of your graph is similar. So this is just giving us a rough idea. So that the strong acid, we see not much happening initially because we have a neutral conjugate. We just make sodium chloride. And then we get our sharp change, and then post equivalence, it's the same. All right, any questions? I got 2 more pieces. So we're gonna skip and do a couple of these steps. So initially, the type of, oh, it's an x squared. Why is it an x squared problem? There's only one thing present. There's only one species present because you have only the weak base. So you're going to have Kb equal to x squared over the 0.1 molar. All right, here we go. So somebody else can get up there. If you're up yesterday, that's your point. That you can still answer. You can take a deep breath, see if somebody else can answer. When else on this page is it x squared? Anybody?
Equivalence?
It is. At the equivalence is the other x squared point. That's actually, I'm impressed. So initial and equivalence are x squared problems. All right. So our reaction, we're starting with the NH3 plus the HCO. This is a question, I think, Major, you asked me last night. So in this reaction, because this is something that happens, I think, on the worksheet, the NH3 and the HCl, the whole thing just kind of combines to NH4, which technically has a positive, and the Cl negative. Now, we're technically in aqueous solutions, so they're actually separate, but we just usually show it together, and that's our only product. Now we would do the mice chart. And I'm going to pause us and give you 5 minutes. You can try this one. You can try the half. You can try any of them you want. All right. Or you can take a break for 5 minutes. So is that, all right. Question. Somebody wants to go for it. Again, I'm going to be asking why the answers make sense. So if you went through solving, right, this one, your X was your hydroxide. Just a reminder, going back to the X, the first one, because it's Kb. So if it's a Kb, your X is your hydroxide. So you have that extra step. So when you do the negative log you'll be at POH, and then you'll give me that, and then you'll change it, because I'm going to always ask for pH. The answer makes sense because it's a weak base, so the pH is high. So it's a weak base, so pH should be above 7. To start with, it should be quite a bit above 7. And then we start adding. This is in the buffer zone. So here, once we start adding, we're in the buffer zone. So we're looking at the Ka exponent, or the, yeah. You can look at the Kb exponent and then do 14 minus that. So we should be around 9, and we are. If you like that little trick, you can think about it. All right, our equation, our mice chart. So 0.05 liters times our 0.1 molar. This is, some of you are probably, all of you are probably thinking, she's so nice with us, these numbers. I'm being nice to myself, not to any of you. But it's good to work with all those crazy numbers I give you. And then the HCl is here, so 0.02 liters, and its concentration is the 0.1. A reminder, for titrations, you have a 0. For buffers, today's study set and worksheet, there's no zeros. Also a reminder, no equation. You're not writing the reaction until you see HCl or NaOH. Then you're writing it. This is not the equilibrium expression. That's why it's a mice chart and not an ice chart also. This is a limiting reactant. And right, our limiting reactant is going to typically be the strong acid or strong base. And then label, this is my weak base. NH3 is the base. This cancels, and over here, this is, you can just say acid or conjugate acid. So this is back to the question that came up during my office hours. This is a buffer because we have both pieces. You can switch to Ka, or you can keep using Kb. It doesn't matter. Just make sure you label it, that you're showing your steps. So if you're using Kb, this is conjugate acid, this is the base. If you're using Ka, this is the acid, this is the conjugate base. Something Max did, he tried it both ways on some problem from yesterday, and it will come out the same. All right, the half equivalence. What is equal at the half equivalence? Well, your moles or your molarity of your halfway. In this case, the weak base, or the NH3, is going to be equal to its conjugate acid, so the NH4. Another way of thinking about it was most students just simply state the pH equals the pKa. That's all you have to do there. So if you didn't switch to pKa or to Ka, you would here. So here's my question. What if you just went with the pKb? What's the pKb going to be equal to at this point?
POH, and then you
Yep.
switch.
Yep. Yeah, so this is the point where there's all these possible things. So I don't give you a lot of space because all you have to state is this: the pH equals the pKa. There are some people who like working with the KBs, so you can also do that. Just realizing what I cut Christian off there from, it is the POH, so then you would have to switch it to the pH. All right, let's do the equivalence point. So you can write your whole mice chart, or we can do an abbreviated. Our initial here of the HCl is always this 0.005 moles. That number doesn't change. By the way, a reminder, x squared, that's molarity. So we're going to get there. Here, this is also 0.005 moles. You can write the whole chart and show that they cancel, or you can just cross them out. I'm okay with that. It's all over here now. It's x squared. You must use Ka. because only the acid, only the conjugate acid is present. It's an acid. When it's an X squared problem, it matters. So we have to be Ka equals X squared, and we have to be molarity. So as promised, I'm going to make sure, because on the next page, we have to solve for volume. So the way you find the volume of the HCl, and you can have space, you can do it up above. I usually have an extra step for you to show it. I've learned that over the years, that you know the moles, because it's the same. This is the only step where we know the moles. If you take moles and you divide by the molarity, this is the molarity. So we're dividing by the molarity. You can just show it as one step with the units. So moles divided by molarity, and see the moles cancel. So in the factor label, that 0.1 is on the bottom. So that's how I get the 0.05 liters. And my initial for the NH3 was 50 milliliters, change it to liters. So this will be 0.1 liters total. You do that. All right. And then when you do this one, you're going to find you have excess HCl. So your post-equivalence. Just, I need to do the next page, and so I'm seeing the time. So you can try it on your own. When you have excess HCl, you're just no Ka, no Kb. It's just the HCl. If you have HCl, you have the NaOH, you're after the equivalence, no Ka, no Kb. We just go straight into the, but you must be molarity. You just do negative log of the excess. So the excess moles, you do your mice chart. You find these moles, and you have to divide by the total volume. All right, we're going to do a real quick curve. I'm going to go back to here so I can draw it. It's basically, it's a similar idea, except flipping it. This is, we're going to add HCl volume. And I'm going to do this really brief. We'll see one at some point where we'll put more detail. You're going to be going gently, and then the cliff drops. So this is like Max is mountain biking, going, oh, I'm having a great time. Look, I can go no handlebars. Wow, my bike is messed up. And he's going down the slope, or you could be kayaking, and this is the waterfall. There's our equivalence. So gentle slope straight down, not less gentle straight down. It's a cliff. And then we flatten out. You could also do a kayak. Kayak would have worked really great there, because this is where we have excess. It's not perfectly flat. The cliff is not there's no perfect cliff, is there? All right, there probably is at the top of Everest, straight down on each side. All right, we're going to look at the last page. I wrote a comment to myself. So I am going to open next week's folder. It is not complete. It's going to have the next study set and worksheets. This is lab for next Friday. It is due. Did not know this until I posted it yesterday, on Friday the 13th. I could not have planned that if I had tried. It is 4 pages of titration calculations. It is there. if you want your Friday the 13th to go do whatever you do on Friday the 13th, yeah, take a look at it before Friday the 13th. It will be there the whole week. It'll be there after this class is over. It's all calculations. And so next Friday, I will be having office hours. But all right, your worksheet is like 1 or 2 pages of calculations. This is to make sure when we get to the celebration the following after the weekend that you've got it, you can do it. The other lab due next week is the one where you guys are all meditating and giggling or whatever you're doing. All right, let's go through this. Acetic acid is, I always write it as the week first, just because I'm in that habit and to be consistent. It doesn't matter. So that's acetic acid is a CH3CO2H plus the NaOH. All right. You're going to do a mice chart. Just doing one. For this one, I'm going to pause in a moment. I'm going to give you a chance. You can try one or both of these. This is Hockle, that's Cl. And we're reacting it also with NaOH. So this is the hydrogen and the sodium are going to switch. So we would show Na Hockle. And then the H and the OH will make H2O. You can show the H2O or you can leave it off. That will be the same equation at the equivalence. I'm going to pause us. Try one, whichever one you want to try. I'm going to walk through the first one. And so add 90 milliliters of the NaOH. You see a strong, you write your equation. And again, you can show the sodium first or last. Sodium's not going to matter. So that's going to be my M is the volume times molarity. So remember, you can take your milliliters, you divide by 1,000. That will give us our liters. And then there's for my acetate, so 0.010 moles and 0.009 moles. Reminder with titrations, you have a big fat 0 to start with on your product side. For buffers, there's always numbers on both sides. All right. NaOH is my limiting, so subtracting the 0.009 on the reactant side, and we'll add it to the other side. All right, so that cancels. You don't have to show the math of the 0 plus the 0.009. It's just there. Here we have 0.001. Please notice we have the units. And again, if you want, you can put all your columns. You can show all those steps so you have everything there. And then labeling. This is my acid or my weak acid, and this is the conjugate base. My question for you, where are we in the titration?
The buffer zone.
We are. We're pre-equivalence. So this is pre-equivalence before the equivalence, which is the buffer zone. And actually, I like that better, the buffer zone. We know that because our limiting reactant is the strong base. But that tells us that when we get to a pH, and it's that we can see, okay, we're in the ballpark. Yeah, the Ka we had used on a previous page, or a reminder if for some reason I left it off. Sometimes that happens on the study set or something. We have them in our notes from last week. So 5, we're in the zone. We're really close to equivalence, so it's starting to get to the point where the cliff is going to go straight up. Okay, so that's my pieces. You can state your formula. You will state your formula. Conjugate base, hydronium over the acid. Labeling these really will help you. So you make sure you put them in the right level. So the 0.001, why can I keep it as moles?
Because they're both as small.
Yeah.
They're equal volumes. It's a ratio. They both cancel. If you see that, that's a wonderful shortcut, saves you some time. If you're unsure, you can just always then divide by your total volume. But once we plug everything in, our only x, right, we'll have our 1.8 e to the negative 5 equals 0.009. As long as they're the same unit, we have moles, This is x and 0.001. Cross multiply, your x is your hydronium. And yeah, you should get the pH with 5.7 is up there. And so we're in the buffer zone. Our pH should be in the range of our exponent, but we're getting really close. We're almost at the equivalence. Any questions?
Yeah, what makes them the same volume? Like I got the right answer, but I thought they were different volumes. 90 milliliters of the NaOH.
The NaOH is gone. What I'm saying has the same volume. So if actually, and I want to emphasize that, so thank you for asking that, is at this point, we're supposed to go to molarity. I would divide by the total volume.
Right.
And so you'd have to add the 90 and the 100. So you would be dividing them both by the 0.19. So again, that has to be the total volume. So this would be dividing them both by the 0.19. It's going to change the number, but the ratio would not change. You got it now?
Yeah.
Yeah. So you can only do that if it's a buffer where you have these two pieces. X is molarity. It's just this volume here cancels, not that volume.
Right. Yeah, I got it. I think, I don't know.
You're good. Thank you. Actually, thank you for that question because I should have showed that to remind people. And if you're not sure, please ask or come to an office hour. I am going to have an office hour tomorrow, this Friday. I'll again be there at 1 o'clock. If somebody in the evening group wants me there at a later time because you're working, just talk to me about it. So if you're somebody who wants to start on the titration calculations, which there's a couple of you who like to do that, or if you have questions on the pH lab, that's due tomorrow. And then I will have them next Friday to a different time. All right, the next one, I changed it up a little bit because it's good. I started us with mass. So we're just taking the mass, the 0.35 grams, and this 52.5 I got from our handy dandy periodic table. So I added up the HCO and the Cl. So grams, 1 mole over that many grams, and we get another 0.00667 moles. So show your zeros. I recommend for most students, it's better to write it out longhand than say 6.67 times 10 to the negative 3, but you can say it that way. And if it helps you to put the 0 before the decimal, please do that. And then this one, we would have our volume. This is the information that goes together. The of tells you those two pieces go together. The 50 milliliters we're going to need when we do our total volume. We actually don't need it on part A. We'll need it on part B. So this one is 0.018, 0018, sorry. And this, of course, would be a 0. All right. Do you want me to give you a few moments to try it? So while you're trying that, I'm going to pause this in a moment in case some of you are really fast and want to try both or just want to try the second one. What number, only one number from up here goes in the chart here? Which number?
0.00667.
Yes. Moles. That number is for this whole titration because it's what you started with. That's the initial amount of the Hakel. If you're at equivalence, because I didn't say anything about that, all I did is say figure it out. All you need is this number because at equivalence, that is the NaOH, that is your change that ends up being over here. So I'm going to pause this again, try it, see what you can do. And if you're watching at home, pause it and try it.